This work is done in Professor Pei Yucho's lab in UCLA Mechanical and Aerospace Engineering, as well as a collaboration with Dr. Daniel Clemens and Dr. Bayu Li in Medicine Department. The outline of this talk starts from reviewing state on microfluidic single-stream focusing, which will include sheath flow focusing and sheath flow focusing. Then basic background on directional forces will show how this technique is used in sheath flow focusing. At the same time, the key problems that have trapped the researcher for years will be pointed out. Then the design concept of how we solve the problem will be proposed. After that, the result will show how to fabricate the device and show the focusing performance. Finally, I will come to the conclusion to conclude this talk. This is an example of the conventional flow cytometer. The system is composed of the several photodetectors which can detect Bohr scattering, side scattering, and fluorescent signal from individual cells. This is a very powerful tool for biologists to study individual cells in a very high throughput way, normally over 10,000 cells per second. To obtain the consistent signal level, all the incoming individual cells has to be well focused three-dimensionally by hydrodynamic sheath flow in the capillary tube. However, the requirement of sheath flow will decrease the throughput of the system, which highly accuracy data is needed. In addition, this standalone system is weak in upstream and downstream integration. By borrowing the microfabrication technology, people have been trying to solve the problems encountered in conventional flow cytometry. Our group have demonstrated the microfluidic fluorescent activated cell sorter by using two-dimensional sheath flow and three-dimensional sheath flow focusing. For two-dimensional sheath flow focusing, particles are focused laterally but not in the vertical direction. Although this device can be fabricated easily by single-layer soft lithography, but the unfocused particle in the vertical direction, they can travel with different speed. It turns out that you can have the detection signal accuracy issue. So we introduced another sheath flow in the third dimension and showing here. So particle firstly get focused in the vertical direction and the lateral direction. In such way, we can focus particle in the single stream. However, the introduce of the excessive sheath flow will dilute the sample a lot. Also, this device will require a complicated multi-layer PDMS fabrication technique. To eliminate the need in sheath flow for particle focusing, people have been working in two different approaches to achieve this goal. One way is called passive focusing, which utilizes the flow phenomena only in high-speed flow. Normally, a microchannel with this kind of step structure is used to induce secondary flow to microparticles into a single stream. However, this approach is very sensitive to the particle size and the medium condition, which fail in small particle focusing. And the requirement of high-speed flow is not always the case in microfluidics. Another way called active focusing, which utilizes external surface acoustic wave to control the particle position. In this work, two sets of interdigit electrodes are patterned on the piezoelectric substrate. When a surface acoustic wave is generated, the leakage wave will propagate into the channel and interfere to form a single pressure node in the middle of the channel. However, this approach requires precise alignment between your channel and your electrode, which is challenging for high-speed flow focusing, the one requiring long-distance alignment for ultra-long interaction distance. And it will be challenging when working with small particle focusing, which may burn your substrate when you apply very high voltage. Directional fluorescence, also called DEP, is widely used in biological sample manipulation in microscale. The equation shown here is a basic governing equation for the DEP force acting on the directional particle. Particle can migrate to different locations of the E field depending on polarizability more or less than the surrounding medium. Traditionally, E field distribution is generated by pattern electrode on the substrate. In addition, DEP force is normally at tens of piconewton range and is highly dependent on particle size, as shown here, and the E field gradient. So for the DEP force, it will become very small when particle becomes very small. By using DEP, people already demonstrated by sandwiching an open insulation layer, sandwich and align between two conductive substrates. So single stream focusing can be very well focused for the particle into a single stream. However, when running in high-speed flow, extremely long interaction distance will be required for reasonable applied voltage value, which is challenging for the fabrication requiring long-distance alignment. In addition, high voltage required for small particle manipulation may induce electrolysis, which will generate a bubble at the edge of the electrode and block your flow in the microchannel. So this is a schematic of our device, which solves all the limitations I just mentioned in DEP single-stream focusing. The DEP manipulation plane is always kept perpendicular to the flow direction. This is what we propose as the flow decouple concept, which decouples the E-field plane out of the flow direction. Second, we fabricate a large area single-layer PDMS thin film sandwiched between two conductive patternless substrates without the alignment. Third, the simple channel is deformed by two high-speed ratio sidewall formed by PDMS. So once you have the pressure at the sidewall, you can actually deform the channel to change the cross-sectional geometry of the channel. So by changing the cross-section of the geometry of the channel, that's what change the maximum E field self-line right at the center of your channel. So how to fabricate this device? We start from standard photolithography to pattern SU-wave photoresist on silicon wafer. And then we prepare a PDMS stamp called hybrid stamp, which has a plastic sheet embedded inside at the bottom surface. The zoom-in view shows the structure of the hybrid stamp. We have a plastic sheet embedded at the bottom surface, but we still have a very thin layer of plastic sheet, a very thin layer of PDMS thin film beneath the plastic sheets. So this is the key of this fabrication. And we pour uncured PDMS on the mold and press each other with sufficient pressure that can repel uncured PDMS on top of the mold structure, but still remain the contact surface to be flat. After PDMS thin film is cured, it can demold while attaching to the hybrid stamp as a support, as is shown here. After that, you can do oxygen plasma treatment to bond your thin film to a conductive substrate. And then after remove your hybrid stamp, you can bond another conductive substrate, and then that will finish your fabrication. So in this fabrication, you need zero alignment because your substrate have no pattern electron on top. So this is a fabricated device which has one simple inlet, one simple outlet, and two pneumatic pressure channels to control the sidewall profile. So I can see to the right, as you change the cross-section of the geometry, all the E-field line will cross at the neck, but this is where the highest E-field strength is. And also this is right at the middle of the channel. So as the simulation result shown here, flow direction goes to the top. So without changing the voltage here, you actually, by changing the cross-sectional shape of the geometry, you dramatically increase the E-field gradient of your channel structure. So this is a video showing that I apply pressure on the top and the bottom channel. So under different pressure, you can start to see the channel big deform. So the gap between the sidewall will eventually get fully touched and close each other under 60 psi. So this is the reference curve that we obtained during the experiment, which is the reference point that in our experiment. So in the focusing test, we start from large particle size, which is the mammalian GFB heat cell line. Each individual cell has a diameter around 15 micron. With the median conductivity and applied voltage shown here, we pump the sample into the device with average flow velocity around 17 centimeters per second. When operated without sidewall deformation, we observe no focusing at all. As we pressurize the side channel under 35 psi, the sidewall gap is around the size of the cell. DP force can attract all the individual cells to flow into a single stream. So to demonstrate the tunable focusing, we keep the voltage and flow rate at the same level, but we change to much smaller cells. In this case, we use GFB E. coli with the size around 2 micrometer in length, 700 nanometer in diameter. Again, there is no focusing when no pressure is applied to the side channel. But as the side channel pressure increased to 52 psi, the sidewall gap is around 3 micron. the bacteria was tightly focused and flowing along the flow. This is a proof that without increasing the voltage, we can still have a very tightly focused performance in high-speed flow by changing the cross-sectional shape of our channel. So for smaller particles like GFB like vacuum strand shown here, and 100 nanometer red pouring starting beads, tight focusing streams are achieved with average flow rate at 2.1 centimeter per second and 3.5 millimeter per second respectively. From the results shown here, this platform can provide very efficient scissor single stream focusing of ultra-large range on particle size in high-speed flow. So the size can range from 100 nanometer all the way up to tens of micrometer. And the flow rate Reynolds number can go from very low Reynolds number all the way up to tens of it. To conclude this talk, this platform successfully demonstrates tunable scissor 3D focusing in high-speed flow. This is a single-layer, large area open pigment thin film sandwiched between two patternless conductive substrate. The flow decouple concept is realized by the beauty of self-aligned tunable sidewall deformed along the entire channel. Particle size ranging from 100 nanometer all the way up to tens of micrometer in high-speed flow over Reynolds number of 10 has been demonstrated. Finally, I will thank all my lab members in Optofluidics System Laboratory, UCLA. I will also appreciate Professor Pei Yu for his long-term advice and support during my graduate study. And this talk is supported by our industrial collaborator and National Science Foundation of the United States of America. Finally, thank you for attention.